Hello, everyone, and welcome to today's Friday Happy Math Hour. Today, we're going to cover sets, probabilities, permutations, and combinations. I believe this is Chapter 8 and Chapter 9 from the 1324. Okay, these are all the topics that we're going to cover today. So let's first start with sets. Okay, what are sets? Set is a well-defined collection of objects. Examples of sets. These are well-defined collection of objects. Number one, all the students in my class, in my math class. That's well-defined. Also, number two, letters in the alphabet. That's also well-defined. Let me show you an example of a set that's not well-defined. For example, the collection of young adults. That's not well-defined because what's considered young adults? Let me make that statement a well-defined set. Okay. If we say the collection of young adults between the ages of 18 to 29, then it's well defined. This is an example of a well-defined set. Capital letters such as A, B, and C are used to name sets. At the beginning of this presentation, I will be explaining like a lot of the definitions and stuff that we need to know, like a lot of the concepts. Okay, before I do examples. So let's continue. Each object in a set is called a member or element of the set. The set braces are used to enclose objects in a set. For example, this means set A equals to the elements 3, 4, and 5. And here's how you read it. Set A consists of elements 3, 4, and 5. The symbol, okay, this symbol looks like an E, but it's not an E, just a symbol. It means it's an element of the set. The symbol with the same symbol as an element, I mean with a slash over it, it means it's not an element of the set. In other words, this first symbol means that the element is in the set, and the second symbol means that the element is not in the set. Example, the set A consists of the elements 3, 4, and 5. We can say 3 is an element of set A, or we can say 3 belongs in set A. Or 3 is an element of the set 3, 4, 5. Okay, and here's the correct way to read it. 3 is an element of the set A, or 3 is an element of the set containing 3, 4, and 5. 2 is not an element of A, or 2 is not an element of the set containing 3, 4, and 5. Okay. Okay, now, sets definition and examples. Empty set. An empty set has no elements. There's two ways to represent an empty set. The first way is like a 0 or like a null with a slash over it. That means empty set, or the brackets with nothing inside. That also means empty set. Equal sets. Equal sets, there are sets containing exactly the same elements. Let me show you an example. Here an example of equal sets. For example, the set 3, 4, 5 is equal to the set 5, 4, 3 is equal to the set 4, 3, 5. These are called equal sets. You see they contain the same elements. Sometimes we describe a set by common properties of its element rather than by a list of its elements. This property can be expressed with set builder notation. And here's how you read it. The set, you see the set of all elements X such that X has a property of P. Okay, let's break it down. The set, okay, this is a set, right, with a curly bar, so the braces. The set, right, which is a braces of all elements X, which is the X, the first X. This line means such that. And here's the property X has a property of P. Okay, now example. List the elements in a given set. The set X the set of all elements X such that X is a natural number more than 5 and less than 8. If it says more than 5, it cannot be 5, right? And also it cannot be 8. So the set will be 6 and 7. For B, the set of all elements x such that x is an integer and is between -3 and 1, right? But here, because the symbol has like a little line underneath it, it means that 1's included. So it's going to be from -2 to +1. Okay, now this you need to know. Whole numbers, they start with 0 and they go all the way to infinity. Counting numbers are the same as natural numbers. They start with 1 and go to infinity. Okay, that's very important to know. Let's continue. Okay, now, these are actually examples from the book, okay, from the homework. It says state whether the statement is true or false. So here, we have to say if it's true or false, and then we're going to explain the reason why. So, for example, 3 is an element of the set containing 2, 5, 7, 9, and 10. That is false because 3 is not in that set. Okay. Look at number 2. 2 is an element of the set containing the elements 2, 5, 7, 9, and 10. This is true because 2 is in the set. Look at 3. It states 6 is not an element of the set containing 1, 3, 5, 7, and 9. That's true because 6 is not in the given set. You see, 6 is not an element of the set. Look at number 4. 4 is not an element of the set containing the elements 2, 4, 6, and 8. That is false because 4 actually is in the set. Okay. Now let's continue with number 5. Okay, let me go back real quick. This is saying the set containing the elements 1, 2, 3, 4 is equal to the set containing 4, 2, 3, 1. That's true because every element in the first set is also in the second set. So that's true. Both sets have the same elements. Look at number 6. The set containing elements A, B, and C is equal to the set containing the elements A, B, C, and D. That's false because the first set does not contain the element D. Number 7. All the whole numbers greater than 5 and less than 9. Let me see all the numbers greater than 5, which means it's going to be 6, 7, 8, less than 9. 9 is not included nor the 5, so this is true. And there's the reasoning behind it. Greater than 5 and less than 9 means the whole numbers between 5 and 9. Number 8. It states all natural numbers, the set of all natural numbers not greater than 4 is equal to 0, 1, 2, and 3. This is false because 0 is not a natural number. Remember I mentioned earlier on the previous slide that please know that the natural numbers start with 1 and they go all the way to infinity. And whole numbers start with 0 and go all the way to infinity. Look at number 9. Number 9 reads like this. The set with elements x such that x is an even integer between 5, right, 5 is included, and also 19 is included between 5 and 19. Okay, we have, it has to be an even integer, so we have 6, 8, 10, 12, 14, 16. This is false because the 18 is missing. No, 18 is missing on the set. Number 10, the set of elements x such that x is a vowel equals to A, E, I, O, U. That's true because these are all the vowels, A, E, I, O, U. That's true. Okay. And again, I believe these are homework problems from the book. Subsets and proper subsets. Universal set, a set that contains all the objects being discussed. Now subsets and proper subsets. Okay, and here's a definition. A set A is a subset of set B. And this is how you write it. The symbol for subset is like is this symbol here. Like it looks like a C, like a straight C with a line underneath. Okay, and this is a definition provided that every element in A is also an element of B. I tell my students to always have this definition here at their disposal when they're answering these problems, because at times this can be a little bit confusing, right? I mean, especially when you first when you first are introduced to subsets and proper subsets. So I tell them to always have this handy, this definition. And a set A is a proper subset of a set B, written A is a proper subset, and this is a symbol for proper subset, is like a straight C. If every element of A is an element of B, but B contains at least one element that is not an A. In other words, every element in A has to be in B, right? But B must contain another element that's not in A. That's what it means. When A contains an element that is not in B, then A is not a subset of B. We write it, A is with a slash over it means it's not a subset of B. This is a notation. Okay, now for any set, any given set, okay, here they say set A. The empty set is always a subset and a proper subset of any set. And also a set is also a subset of itself. Let's give some examples here. Okay, example. Set A is equal to has the elements A, B, and C. And set B has the elements A, B, C, and D. And set C has the elements C, A, and B. Okay, these are all true statements. Okay, for example, on A is a subset of B. And here's why. Because A contains A, B, C, and every element in A is also in B. That's by definition, right? Here on top, a set A is a subset of set B, provided that every element in A is also in B. You see, every element in set A is also in set B. Look at B. The symbol means proper subset. Every element of A is an element of B, right? So every element here in A is also in B, but B has another element that's not in A. That's a definition of a proper subset. Let's see C. B is not a proper subset of B is not a proper subset of A. That is very true because every element in B is not in A. Let me go back. Look at D. A is a subset of C. This is true because every element in A is also in set C. E. A is not a proper subset of C. This is true, right? Because A is not a proper subset of C because they're both equal to each other. These A and C are equal sets. And lastly, F. The empty set is a proper subset of A. That's true because every set contains the empty set as a proper subset. Let's move on. Okay, now this is also from, I believe, from the homework. It states, let set A equals to the set containing -4, 0, and 4. And set B contains the elements -3, -2, -1, 0, 1, 2, and 3. And set C contains the elements -4, -1, 0, and 4. And set D contains the element 0. And set E contains the element -4. And this is my universal set. It's the integers between from -4 to 4. So here they're asking to insert the proper subset symbol or not a subset to make the given statement true. Okay, now A, right? So let's go to A here, right? A contains -4, 0, and 4. Let's go to the universal set. So -4, 0, and 4 are also here, right? So this will be the first symbol, which is proper subset. And here's why. every element of set A is an element of U, but U contains at least one element not in A. For number 12, let's go to E. E has the set containing the element -4. Let's go to A. The element is -4 is also here. So this will be also the first symbol, which is the proper subset symbol. And here's the reasoning behind it. Every element of E is an element of A, but A contains at least one element not in E. If you switch them around, right, you put set A, and then we have set E, right? So this will be the second symbol, which will be not a not a subset, because every element of A is not in E. Elements 0 and 4 are not contained in set E. Let's go to set B and set C. Set B contains the elements -3 all the way to +3. The integers. And set C contains -4, -1, 0, and 4. So every element in B is not in C. So this will be the second symbol, which will be the subset with a slash over it. And here's the reasoning behind it. Every element of B is not in C. Elements -3, -2, 1, 2, and 3 are not in C. Number 15, the empty set. Because remember, by definition, the empty set is a subset of every set. So for 15, the first symbol is going to go there, proper subset. Okay. Let's look at 16. The set 0 and 1. Let's look at D. Right. The set D only contains the 0, so this will be the second symbol, which means that the set 0 and 1 is not a subset of D. You see, and every element of set 0, 1 is not in D. Element 1 is not in D. Now, if you reverse it, right, if you put D and then the set 0 and 1, this will be the first symbol, because every element in D, which is a 0, is also in the set 0, 1. Let's look at D and B. D is the set with element 0, and B is the set with -3, -2, -1, 0, 1, 2, and 3. If you notice, the 0 is also in set B. So this will be the first symbol, because every element of D is an element of B, but B contains at least one element not in D. Let's look at set A and set C. Set A is -4, 0, and 4. And set C is -4, -1, 0, and 4. So this will also be the first symbol, because every element that's in A is also in C, and C contains an element that's not in A, which is a -1. Well, anyway, guys, this is how you read this, and and like I said, this is actually from the homework. Okay, now subsets. It says here, list all the possible subsets for each of the given sets. Let's start with A. Recall, a set A is a subset of set B, right? And this is my notation. A is a subset of B, provided that every element of A is also in B. So the empty set is always is a subset of every set. So the empty set is included. Now, like I tell my students, you always let's pick one at a time. So the set 4 is also a subset of the set 4, 6. And then we use this the 6, the set with element 6 is also a subset of 4 and 6. And then we put them both together. The set containing 4 and 6 is a subset of itself, which is 4 and 6. So there's going to be 1, 2, 3, 4. So there's going to be 4 subsets. Let's look at B now. You see the set with 2 elements has 4 subsets. So for B, again, we start with the empty set. And then we start with one at a time, right, with one element in the set. So the set A The set with elements A is a subset of the set A, B, and C. So is the set B, and so is the set C, right? And now we put them with pairs. So the set containing elements A and B is a subset of the set A, B, and C. The set containing elements A and C is a subset of A, B, and C. And then we use the set containing B and C is a subset of the set A, B, and C. And lastly, right, we put them all together because every set is a subset of itself. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8. This is important because this is leading. If they ask you to list them, you have to put them in this form. But if they say how many, by the pattern, guys, this is a pattern. This is a definition of how. If they ask you how many, say how many subsets are in a certain set. So this is going to be 2 to the nth power. For example, for A, right, there was 2 elements, so it'll be 2 squared. That's why it's 4. For B, there was 3 elements, so that's my n. So n is 3, so it'll be 2 to the 3rd power. That's why it's 8. That's how this definition is explained. Look at number 20. Find the number of subsets of the given set. So it's only 1 element, so it's going to be 2 to the 1st power, which would be just 2. Look at 21. There's 3 elements, so it's going to be 2 to the 3rd power, which is equal to 8. 22. The set with elements x such that x is a whole number less than 5. Remember, whole number means it's going to be 0, 1, 2, 3, 4. So there's 5. So that'll be 2 to the 5th power, which will give us 32 subsets. Okay, now comes operations on sets. A given set A and a universal set U, the set of all elements of U that do not belong in A is called a complement. The complement of A is written A with a comma, with a little what's this called? Yeah, well, that's called prime. You'll see with a little like a comma on top. It's called prime or not A. The complement of A is called not A or A prime. For example, the universal set has the integers from 1 to 12, and set A has the integers from 1 through 4. So let me give you a Venn diagram on how this is showing. U is every element, right, that from 1 through 12 has to be in here. You see, these are the only numbers being considered, or the only elements being considered. So let's call this set A. So the complement of A is all the elements not in the set A, so it'll be out here outside the circle. Now, let me show you how it's done with the actual numbers. Find the complement of A. The complement of A means not 1, right? Not 2, let's scratch it out. Not 3, and not 4. Scratch it out. So what's left? 5, 6, 7, 8, 9, 10, 11, 12. Again, the complement of A, which means not A, means not 1, not 2, not 3, not 4 from the universal set. So the answer will be 5, 6, 7, 8, 9, 10, 11, 12. The set containing all those elements. Now, how can it be represented in a Venn diagram? So this is the universal set. So set A, right, this is my set A, contains the elements 1, 2, 3, and 4. That's set A. And the complement of A will be all the elements that are not in A will be here in the outside, the circle, but inside the actual rectangle. It doesn't matter where, but they're going to be outside the circle, but inside the rectangle. There's the 5 to the 12. Okay, now we're doing intersection of two sets, which means and. And means intersection. Given two sets, A and B. The set of elements belonging to both set A and B is called the intersection of the two sets, written as A, right? This means like the upside down U. A intersects B. Elements belonging to both sets. But I like to say at times students have a hard time trying to understand that. So that's what I say. I try to make it like an easier way. So what I tell my students to is what do they have in common? That's intersection or and. Example. The same as before, right? Same universal set. The elements from 1 through 12. Set A contains the elements 1, 2, 3, 4, and set B contains the elements 2, 4, 6, 8. So let's find A intersects B, which means what does set A and set B have in common? They have in common a 2 and a 4. So it will be the set containing elements 2 and 4. How can we represent that in a Venn diagram? This is my universal set. This is set A. This is set B. So the intersection will be here where both sets intersect, right here in the middle. Okay. And let's do it with the numbers, with the elements. That's set U. So set A, right, what they have in common will be the 2 and the 4 has to go inside here. And then after that, right, this is set A is going to contain, so the 1 and the 3 has to go right here. You see set A contains 1, 2, 3, and 4. Now set B contains, right, we have the 2 and the 4 there already in set B, so 6 and 8 has to go inside the circle, right, but not where they intersect, 6 and 8. Now we have to take into consideration the numbers that are not in set A and B, right? They have to be here in the outside of the circles. So we have 1, 2, 3, 4. The 5 is missing. So let's put the 5. We got the 6. We need the 7. We got the 8. We need the 9, the 10, the 11, and the 12. That's how you represent A intersects B with the given elements for the universal set and the elements for A and B. Disjointed sets. Disjointed sets means they don't have nothing in common. They don't even touch. Okay. For example, again, the similar universal set as before. The set containing the elements 1 through 12. A, it contains the elements 1, 2, 3, 4. And B contains the elements 2, 4, 6, 8. And C contains the elements 5, 7, 9, 11. So find A intersects C. What do the sets have in common? They don't have nothing in common, so it'll be the empty set. Nothing, right? Empty set, which means they do not intersect at all. That's set A, and here's my set C. Now, again, this is my universal set. That set A contains the elements 1, 2, 3, 4. That's my set A. And set C contains the elements 5, 7, 9, 11. So the rest that are not in these two on A and C have to go outside the circles, but inside the rectangle. So what's missing? We have 1, 2, 3, 4, 5. The 6 is missing. There's 7 with the 8. We got the 9. The 10 is missing. We got the 11, and the 12 is missing, so it's going to go on the outside. So this is how you represent the situation here. Okay, that A intersects C in a Venn diagram. Okay, now comes another symbol. Okay, this means the or, like the U means the or, like the upside down. The symbol here means the or. In two sets A and B, the set of elements belonging to sets A or B is called the union of the two sets, written as A union B. Okay, now here's my definition at times to the student, because at times some of the wording from the book is kind of hard for the students to understand, so I have to come up with an alternative way to explain the material. So this is what I tell my students. You're gonna list all the elements of both sets, but do not repeat them. Okay? Example. The same sets as before. So A union B. Okay, here's what it means by list all elements of both sets, but do not repeat. So since A is first, I'm going to put everything in A, right? It's 1, 2, 3, 4. Then I'm going to go to set B, right? The B contains the elements 2, 4, 6, 8. So we go to 2, right? Because 2 is my first element. Is 2 already in the set A? Yes, it is, right? So we don't write it again. How about the 4? Is the 4 already in there? Yes, it is. How about the 6? No, so we have to put the 6 down. How about the 8? It's not there, so we got to put the 8 down. That's how you represent A union B or A or B. Now let's do it in a Venn diagram. There's my universal set. This is A, this is B, and these both together will be A union B. Let's put that in with the elements. That's U. So first, we're going to start right where they intersect. So it was the 2 and the 4. They go there. Right? The 2 goes there. The 3 goes there. And the 4 also goes here, right, where they intersect. Then we go to set B. We already got the 2, the 4, so the 6 goes there. The 6 and the 8 have to go in there. That's how you represent A union B. But now what's missing? We got the 1, 2, 3, 4. We got the 5. It's going to go outside. The 7. We got the 8, the 9, the 10, 11, and 12. That's how you represent this the A union B in a Venn diagram. Now comes operation on sets. Let A and B be any sets with U signifying the universal set. Then the complement of A is written as, right, A complement or not A. And here's how you read it. The set elements of X such that X is not an element of A and X is an element of U. This is to recap what we just did right now. The intersection of A and B, okay, that's how you write it, and here's how you represent it, right? This means intersection, and in a similar manner, the union, right? Both A and B are going to be shaded. And how you read it is the set with elements X such that X is an element of A or X is an element of B or both. Now comes the exercises. Okay, now this is given. The universal set is A, B, C, D, E, 1, 2, 3, 4, 5. Set X contains the elements A, B, 1, 2, 3. Set Y contains the elements B, D, 1, 3, 5. And set Z contains the elements B, 2, 3. And again, these are from the homework, from the actual book. Okay, since we have to find the complement of X, the complement of Y, I'm going to put everything here. So it'll be easy to get the answers for each problem. So that's set X, right? So the complement of X will be C, D, E, 4, 5. Because the complement means we go to the universal set. So it's not going to be not A, not B, not 1, not 2, not 3 from the universal set. So this is what's left, C, D, E, 4, 5. Same thing with the set Y. The set Y contains the elements B, D, 1, 3, 5. So Y prime or not Y means the elements from the universal set, which means not B, right? Not D, not 1, not 3, not 5. So what's left from the universal set is a set containing A, C, E, 2, and 4. Now, so we don't have to get the complement of Z, we just put Z there. Okay, so now let's begin getting the answer for number 23. It states X intersects set X intersects set Y. So what does set X and set Y have in common? They have in common a B. Let's see, a 1 and a 3. And that's it, right? Because that's what they have in common, these two sets, X and Y. So that's my answer. Number 24, X union Y or X or Y. Okay, again, like I mentioned in the previous slide, when you have union, you're going to write all the elements of X first, which is A, B, 1, 2, 3. And then we're going to go to set Y. If it's already in there, we don't write it again. Is B there? Yes, it is. So we don't write it again. How about D? No, it's not. So we have to write the D. The 1's there? Yes, it is. The 3 is already there. The 5's not there. So we have to put in 5. So that's my answer right there. But the back of the book, they always have them in order from in alphabetical order and also from the numbers from least to the greatest. If you put this as the answer on your MyMathLab, it still will kind of right because these are the same. These are equal sets. For number 25, we have the complement. The complement of the complement of X is already here. We already answered it here on top, right in red. So it'll be the set containing the elements C, D, E, 4, 5. Now, number 26, what does the complement of X and the complement of Y intersect? So let's go here. So it's going to be intersect. Let's see the C. So it's going to be C, not D, E, and the 4. That's your solution. Okay. Number 27, the complement of X union Z. So it'll be here on the right, the complement of X union Z. They don't have nothing in common, right? Because they don't have a C nor a D. E, 4, 5. They don't have nothing in common, so it's going to be the empty set. That's your answer. Okay, now number 28. Right, so here we have to follow PEMDAS, right? So first we have to follow the Y intersects Z, the set Y intersects Z. So that'll be first. So let's put right. So let's put what does Y and Z have in common? The sets they have in common a B and 3. B and 3. B and 3. So then now X union the set B and 3, I mean the set containing the elements B and 3, like I mentioned earlier, we're going to put everything in X first, right, which is A, B, 1, 2, 3. And then we go to the set containing the elements B and 3, right? So the B is already there, so we wouldn't write it again. And the 3 is already there, so we wouldn't write it again. So this is my answer right there. A, B, 1, 2, and 3. Well, anyway, this will help you with some of the homework problems that are from the book. Let's continue. And I believe this is from 8.2, which you have three sets all together in a Venn diagram. Okay, this is example, this is number 29 so far. From the Venn diagram, list a universal set U. So set U, guys, is going to be all the elements here. So it's going to be A, B, C, D, E, F, G. A, B, C, right? It's all the elements that are inside the set here. Now, set A will be A, D, E, G. Set B is going to be B, D, F, G. And finally, set C will be C, E, F, G. Okay. Okay, now, what's next? What does A intersect B? A intersects B. Let's see, this is A, and this is B. This is going to be DG. Okay. Now, A intersects C. So this is my A, and this is my C. The sets. What do they intersect will be E and G. Now, finally, not finally, we have to do first B intersects C. So we go to set B, which is right here, right? And C. So what do they have in common, or where do they intersect? It will be FG. And finally, guys, where do the all sets intersect? Will be right here, where they all have in common will be the G. That's how you do. That's how you read a Venn diagram and get all the sets and the intersection and the union, and then also where they all intersect. This is how you read the Venn diagram. Okay, now, again, this is actually, I believe, similar to our problem from the homework. It says 60 people were contracted and responded to a movie survey. The following information was obtained. It says 6 people like comedies, dramas, and science fiction. 13 people like comedies and dramas. 10 people like comedies and science fiction. And 11 people like dramas and science fiction. 26 people like comedies. 21 people liked dramas, and 25 people like science fiction. So they want you to use, for A part, use a Venn diagram to illustrate the survey's results. Okay, so they want us to construct a Venn diagram. So let's do that. There's my 3, because 1 is for comedies, dramas, and science fiction. So let this one on top. Well, anyway, this is my universal set, right? There's 60 people, so it's going to be 60. But let's call this one here the set C be comedies. So this will be my C set. Let's see, let D be dramas. So this will be my set D. And let S stand for the science fiction set, which will be my last set here to the left. Okay, now. So when you have something like this, guys, you always start where all 3 sets intersect. So 6 people like comedies, dramas, and science fiction. So it's going to be right this part right here. Right here. After you do that, then you go with intersection, which means 13 people like comedies and dramas. So let's see, comedies and dramas is going to be C and D, right? So it's going to be these 2 sets here. So this here has to be 13, right? So we already got 6, so this has to be 7, right? Now, it says 10 people like comedies and science fiction. So comedies and science fiction will be this area here. Comedies and science fiction. So this has to equal to 10. We got 6, so this has to be 4. Right there. Okay, now 11 people like dramas and science fiction. So dramas and science fiction will be this set here, and science fiction will be this one here to the left. So this space here has to be 11, right? So this is 6, so this has to be 5. There we go. Now we go to set C, 26 people like comedies, which means all this in C and set C must equal to 26. We got 4, we got 6, so that's 10, 17. So 26 minus 17 will give us 9. So 9 goes here by itself. Now it says here 21 people like dramas. So dramas is the set here on the bottom right. So it's saying 20, let's see how many, 21 people. So we got 11, 18. So this has to be 3. There we go. And lastly, 25 people like science fiction. So all this set S on the bottom left has to equal to 25. We got 4, we got 6, so that's 10, 15. So this has to be 10. That's 10. Now, we're almost done here, right? So lastly, we have to state what's outside the circles but inside the box, which means there were 60, right? So we have to add all this up and subtract the number from 60 to see how many are here in the outside. So we got 9 plus 7 plus 6 plus 4 plus 3 plus 5 plus 10, which is all these numbers here, gives us 44. So X is equal to 60 minus 44, which would be 16. So X equals to 16. That's the answer for part A. Okay, now for part B, it's saying how many people surveyed like comedies, but neither drama nor science fiction. Okay, so let's use the Venn diagram to get the result here. How many people like comedies? So comedies is right here, right? So comedies is right here. How many people like comedies, but neither drama nor science fiction? So neither of these here, guys. So the answer is going to be 9. Here's my answer. For part C, how many people surveyed like dramas and science fiction? Okay, dramas. Let's go again. Drama and science fiction, but not comedy. So let's go to dramas, right? Dramas and science fiction will be these two here at the bottom. Dramas and science fiction, but not comedies means everything, but not these right here, which means it's going to be 10 plus 5 plus 3, which will be 18. The answer is 18. Now, lastly, for part D, how many people like none of the movie styles? So the answer will be what's outside the circle, but inside the box, which will be 16. The answer is 16. Well, this is how you do these type of problems, guys. And like I tell students, you always start where all three sets intersect, and then work yourself backwards. That's how you should start where they all intersect. Okay. Now comes 8.3. This is called Introduction to Probabilities. Random experiment. A random experiment is a process by which we observe something uncertain. After the experiment, the results of the random experiment is known. Sample space. The sample space is denoted by the capital letter S, the set of all possible outcomes of the random experiment. Examples of sample space. For flipping, for a coin flipping, sample space is either heads or tails, right? So it's going to be the S, the set S equals to the elements containing H and T for heads and tails. Rolling a fair die, the sample space is the set containing the elements 1, 2, 3, 4, 5, and 6, because a die has all those numbers 1, 2, 3, 4, 5, 6. There are 6 sides. Okay, now what's an easy way to find the sample space of an experiment? I tell my students to draw a tree diagram. Let me show you what a tree diagram is. It says find the sample space of flipping a coin twice. Okay, so flipping a coin twice, right? So the first flip can be either heads or tails, right? That's my first flip. My second flip can be again heads or tails. So if the first one heads, then it can be heads or tails. And my first flip is tails, then after my second flip can be heads or tails again. So as my sample space will be heads, tails, tails, heads, and tails, tails. There's my sample space. Okay, which would be the set S containing the elements HH, HT, TH, and TT. Okay, now an event. An event is an outcome or a set of outcomes of a random experiment. An event is a subset of a sample space. So for example, if the sample space for flipping a coin is S equals to heads or tails, right? Then one event can be heads, which represents, can be the set containing H, which represents the outcome heads. Okay, checkpoint. Suppose a die is tossed. Write the given event and set notation. The number showing is less than 3. So the set will be, right, 1, right, this is my my set, 1, 2, 3, 4, 5, 6, right? So the event, the number showing is less than 3 will be 1 and 2. Right, 1 and 2. For part B, the number showing is 5, so it will just be the set containing the element 5. C, the number showing is 8. It's going to be the empty set because there's no 8 in the sample space. D part, the die showing is an even number, so it's going to be the set containing 2, 4, and 6. Okay, now here comes, everything is leading up to probabilities. The probability of an event, okay? So this means probability of an event will be the number of the event over the number of the sample space, okay? By this definition, the probability of an event is a number that indicates the relative likelihood of the event to happen or to take place. Okay, the N of E is the number of elements in the event. N of S is the number of the elements in the sample space. Example, checkpoint. Suppose a single FIR die is rolled with a sample space S equals to the elements 1, 2, 3, 4, 5, 6. Give the probability of each of the following events. So for A die shows an even number. So even number are 3 elements. The sample space is 6 elements. So it's going to be 3 over 6. That's my answer, which would be 1/2. For B, the die shows a number less than 10. So less than 10 means it's going to be all the elements because the elements 1, 2, 3, 4, 5, 6 are all less than 10. So it's going to be 6 over 6. The answer is 1. C part, the die shows an 8. There's no 8 on the set, so it'll be 0 over 6, which will be 0. Okay, now another checkpoint. A single playing card is drawn at random from an ordinary 52 card deck. Find the probability of drawing a queen, a diamond, a red card, and a face card or an ace. Okay, a lot of students they don't play cards because but when I was growing up, back in the I'm already like 60, but back in the early when I was young, I used to play cards a lot. So here's the sample of a deck of cards. Okay. I asked my class that if anybody play cards, and some of the young students they don't like to play cards. They like to play other things like video games and stuff. But anyway, all the older people they know about cards. But here I give you guys like an illustration of actual like a picture, so you guys can actually see what's what. So for example, there's 52 playing cards, right? These are called suits. This is the clubs, which are 13. They start with an ace and they go all the way to 10, and then they have 3 face cards, so they have 13 each. So each suit has 13 cards. There will be 13 spades, 13 hearts, and 13 diamonds, which makes it a 52 total. There's 26 blacks, there's 26 red, and there's 3 face cards for each suit. Hey guys, face cards means a card that has a face. For example, the only cards that have a face are the jack, the queen, and the king. So there's 3 face cards for each suit. So there's going to be 12 total. Okay, now let's answer the questions. So let's go with A. Remember, the sample space is 52 because there's 52 cards. So the probability, how many queens are there? There's 4 queens because there's 1 queen for each suit. So it'll be 4 over 52. We simplify, it will be 1 over 13. For B part, the probability of a diamond. So there's 13 diamonds. So it'll be 13 over 52. The answer will be 1/4. We simplify. A red card, right? We know there's 26 red cards, so which is half. So it'll be 26 over 52. And the answer will be 1/2. Okay, now D part. It says a face card or an ace. We know there's 12 face cards, right? Plus 4 aces because each suit contains an ace. So over the sample space, which is 52. So it's going to give us 16 over 52, which reduces to 4 over 13. That's how you do probabilities with a deck of cards. Okay, now we're doing 8.4. This is an actual example from the book. Okay, it says addition rule for probabilities for any events E and F from a sample space S. Okay, the probability of B union F is equal to the probability of E plus the probability of F minus the probability of E intersects F. So I'm going to show you how to use this formula to solve example 1 here. Okay, let's read it. When playing American roulette, the croupier who is attending spins a marble that lands in one of 38 slots. in a revolving turntable. You see there's 38 slots here on the turntable. The slots are numbered 1 through 36, with 2 additional slots labeled 0 and 00 that are painted green. You see here they are, the 0 and the 00. Half or the remaining slots are colored red and half are black. In a roulette, the slots labeled 00 are not considered as even or odd. Now here's what we're looking for. Find the probability that the marble will land on a red or even. Okay, so let me put everything down here. So let the set of red be R. Right? These are, I went ahead and I put here all the elements that are red. All the numbers that are red, which is 1 all the way to 1, 3, 5, 7, 9, 12, and so forth. And then we're going to let the set of event be E, of even be E. So these are the even ones. Okay? So now, let's use a formula. So the probability of red or the red or even, right, that's what we're looking for, is equal to the number of red, which is, right, which will be, let me see here, the red are going to be 18. The even are also, let's see, are also 18. And the red and even, right, for the intersect is 1, 2, 3, 4, 5, 6, 7, 8. That's where the numbers come from. So the probability of red will be 18 over 38. The probability of even will also be 18 over 38 because it's 38 total. And the probability of red intersects even, which was 8 over 38. So it's going to give us 28 over 38. So this is my solution, which simplifies to 14 over 19. That's how we use the addition rule for probability. This example is will help you with some of the homework. Okay, let's do actually some of the homework from here. Example 2. Suppose 2 fair dice are rolled. Find each of the given probabilities. So for part A, right? Again, we use the same formula. So since the first die shows a 2, that'll be the set A. Set A represents the first die shows a 2. Then set B will be the result. The sum is 6 or 7. That'll be set B. So let's give here all the choices, guys. So here's a scenario. So for set A, right, represents the first die is even. So this right here, guys, is set A, the event for set A. And set B will be the sum with 6 or 7. So all these, the sum is 6 across. And below it, all these across are the sum is 7. So there's 36 in the sample space because 6 down and 6 across will be 6 times 6 will be 36. How many are in event A? 1, 2, 3, 4, 5, 6. So event A, the number of event A has 6. How about B, right? So B is going to be 11 because we're going to add them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's going to be 6 over 36 plus 11 over 36 minus where do the intersect is right here, right where the intersect will be there and the 2, 5, which will be 2 over 36. So 6 plus 11 is 17. Minus 2 will give us 15. So 15 over 36 simplifies to 5 over 12. That's the answer for part A. Now part B. Okay. The sum is 11, so we're going to let the set A be the sum is 11. And the set, the second die shows a 5 will be B. Okay. So again, this is 11, right? So it's only 2. And let B represent the event. The second die shows a 5, so the second die is a 5, so it's going to be all these right here. Right, where the 5 is, the second die is a 5. Okay. Which is 1, 2, 3, 4, 5, 6. Where do they intersect? They intersect right here at the 6, 5, which will be 1. So let's put it back here to the formula. It's going to be 2 over 36 plus 6 over 36 minus 1 over 36 will give us 7 over 36. So this is my solution for part B. Okay, now this is the complement rule. For any event E, the probability of the complement is equal to 1 minus the probability of the event. And vice versa, the probability of the event is equal to 1 minus the probability of the complement. Odds. The odds in favor of an element E are defined as a ratio of probability of E to the probability of not E, or the complement of E, or the probability of E over the probability of the complement of E. Okay, observation. Okay, this is how they come with this formula here. Right, so that means the number of the event over the number of the sample space over the number of the complement B over the sample space, right? So we're going to put the first fraction first, which will be the number of E over the number of S times, and then the second one we flip it, right? Because when you have when you divide two fractions, the second fraction, the division becomes multiplication, and the second fraction we flip it. You see the N of S cancels, so we live with the event of E over not E. Okay, that's where the formula comes from. Okay, now this is number 27 from the actual homework on page 434. From now on, I'm going to be doing the actual homework. I know it's already past time, but let me finish this the PowerPoint or the workshop as soon as I can, yeah, because it's crucial for this week, for the week of this exam coming up. Okay, now it says here, a marble is drawn from a box containing 3 yellow, 4 white, and 4 blue. Find the odds in favor in drawing the given marble. Okay, let's do part A. Solution. Right, we have 3 yellow, 4 white, and 8 blue. So odds in favor in drawing a yellow is yellow over not yellow. That's what that means. That's what the N of E means. The N of E over the number of not E, or the complement of E. So how many are yellow? Is 3. How many are not yellow? The 4, the white, and the blue, right? So we add them. It'll be 3 to 12. It will be 1/4. But you write it as 1 to 4. This is the way they want the answer in green. Let's do B. Odds in favor of drawing a blue. It's going to be blue over not blue. The blue are 8, and the not blue are 7. So it's going to be 8 to 7. The ratio of 8 to 7. And finally, C, right? Odds in favor of drawing a white will be white over not white. The white are 4, and the not white are 11. So it's going to be the ratio of 4 to 11. Okay, let's move on. That's kind of self-explanatory. And here comes. This is exercise 47 to 54 on page 435. It says, data from the 2016 General Social Survey can allow us to estimate how many hours people who classified their work status as part-time, full-time actually worked in the last week. Use the following table to find the probability of the event. Okay, now here's solution. Right, so we know that's going to be the probability of the event, the number of the event, or the sample space. My sample space will be, in this case, will be the total, which will be 1,591. So that's my sample space. Okay, so the full-time worker, we go here to full-time worker, will be, the total will be 1,271. So over the sample space, which will give us approximately 0.7989. Number 48, a part-time worker. In a similar sense, right, we still got the same sample space, but the part-time workers are 320, right? Because part-time workers, we go here, 320 over the sample space. We use your calculator, and it should give us 0.2 0.011. Okay, now let's do number 49. Worked hours, work 50 hours or more. So 50 hours or more is gonna, we go here to 50 hours or more is gonna be 393. So 393 over the sample space will give us approximately 0.2470. Number 50. Work zero between 0 to 19 hours. So we go to 0 to 19 hours will give us 106. So it'll be 106 over the sample space. Approximately 0.0666. Okay, on the next slide, I'm going to do maybe two more. Let's do a 51. 51, and let's do one that has a word and one that has a word or. So remember, and stands for what they have in common, right? So let's see here, a part-time worker is right here, part-time worker, and someone who worked 40 hours or more. Okay, so it'll be part-time worker and 40 hours or more will give us, right? So it's going to be these two here, right? Because these two work 40 hours or more, so 49 plus 21, we add them up, it's going to give us 70 over the sample space. Approximately 0.0440. For 52. For 52 says a part-time worker or, right, so that means union or someone who worked 29 hours or less. So for this one, it's best to use this formula because it's a bit tricky here, okay? But let's do this. The probability of, here we go. Why is it 320? It's like this, right? Part-time workers is 320, right? And then union with work 29 hours or less, so it's going to be these two here. That's why it's going to be 106 plus 129 minus where they intersect, which would be 77 and 87. Okay, but this on the right will illustrate it better. Okay, then they represent the part-time workers, and they'd be representing 29 hours or less worked hours. So the part-time workers are going to be, right, the 320, right? These are my part-time workers. And then plus, right, and then my 20 hours or less will be these two here, 106 and 129. That's my N of B, my set B. But then where they intersect will be 77 and 87, right? Because I already counted them here once from the 320. That's why we don't count them twice. That's why it'll be minus 77 plus 87. That's where the 391 comes from. Okay, and again, at times it's better to do it with a formula to make more sense. Okay, so the answer will be 391 over 1591, which would be approximately 0.2458. Okay, now this is 9.2. I believe I have like 3 more slides to go. So 9.2 is called the multiplication principle. Right, so this section will cover multiplication principle, permutations, and combinations. So multiplication principle, here's the definition. Suppose n choices must be made with m1 ways to make choice 1, and m2 ways to make choice 2, and so forth. So what we do is we multiply them out. We multiply the number of ways to make one choice. Let me do an example for it to make better sense. This is number 24 from page 477. It says, how many different heating cooling units are possible if our owner has 3 choices for the efficiency rating of the furnace, 3 options for the fan speed, and 6 options for the air condenser? Okay, here's my solution. Right, so it's going to be 3, right? 3 choices for the efficiency ratings of the furnace. So it's going to be 3 there. So it'll be 3. Number of choices of fan speed, which is also 3. And finally, the options for a condenser will be 6. So it's going to be 3 times 3 times 6. That's how you apply the multiplication principle, which will give us 54. 9 times 6 is 54. So 54 different units are possible. Okay, now here's an example, number 28 from page 477. It says the United States Postal Service currently uses 5-digit zip codes in most areas. How many zip codes are possible if there are there's supposed to be no restrictions, no restrictions on the digits used. So here are two different questions here. So what's my solution? The digits are from 0 to 9, right? That's why there's 10 digits. There's my area code, right? 5 digits. 5-digit zip code. So how many can go here with restrictions? It's going to be 10. Can be in the first choice. 10, 10, 10, and 10. You multiply them out, which would be 100,000. Look at the second question. How many would be possible if the first number could not be a 0? So the first digit cannot be 0. That means this cannot be a 0, so it can be a 1 all the way through 9. So there's 9 different numbers that can go here from 0 to 9. I mean, from 1 through 9, not 0. So then the other digits, the second, third, fourth digit, they don't have a restriction, so it can be any number from the 0 to the 9, which will be 10, 10, 10, and 10. Multiply them out, we get 90,000. Let's do another example. This is number 30 from page 477. It says, for many years, the state of California used 3 letters followed by 3 digits on its automobile license plates. So there's 26 letters on the alphabet and 10 digits that make all numbers. Okay, so here's my scenario. Right, so the first are going to be what, the 3 letters and the 3 digits. So here, guys, they don't have no restrictions, so it's going to be 26 times 26 times 10 times 10 times 10. You multiply it out, and that's your solution, 17,476,000. Now let's do part B. When the state ran out of new numbers, the order was reversed to 3 digits followed by 3 letters. How many new license plate numbers were then possible? If you notice, there's going to be the same thing because here we use a community of property, a multiplication, right? So if we switch the order, it doesn't matter. It's going to be 10 times 10 times 10 times 26 times 26 times 26. We're going to get the same solution as part A. Okay? Now let's see part C. For several years ago, the number described in part B were also used up. The state then issued license plates with 1 letter followed by 3 digits and 3 letters. How many new license plate numbers will be arranged? Will this arrangement provide? Hey guys, check this out. By adding 1 letter in front, okay, the same scenario as part B. Look what happens when you add 1 letter to the license plate. Let's see how many license plates are possible. So it'll be 26 times 10 times 10 times 10 times 26 times 26 times 26. You got 456,976,000. So by adding 1 letter, it went now from 17 million to 456 million. Isn't that amazing, guys? Okay. Okay, now that's how I believe when cars were invented, right? They had to have some kind of license plates. So probably at first they only had like maybe 1 letter followed by a digit or 2, and then as more cars were made, they keep adding more letters and numbers to accommodate every vehicle had a different license plate. I mean, for every state. Okay, now this is the factorial. For any natural number, n factorial means n times n minus 1 times n minus 2 and so forth until you get to 1. And by definition, 0 factorial is equal to 1. Okay, this is what it means, checkpoint. 4 factorial is the same thing as 4 times 3 times 2 times 1. That's what the definition describes here. And B. Oh, and then you multiply them out, which will be 24. For B, 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1, and then we multiply it out, will give us 720. 1 factorial will just be 1. Look at part D. So part D is 6 factorial divided by 4 factorial. So this is 6 factorial, right? So then the 1s will cancel, the 2s will cancel, 3s will cancel, 4 will cancel. So all these are equal to 1. We're left with 6 times 5, which will give us 30. Now comes permutations. A permutation of set of elements is an ordering of the elements. For instance, there are 6 permutations ordering of the letters A, B, and C. ABC, ACB, BAC, BCA, CAB, and CBA. That means that the order matters. For example, ABC, right? The order matters. That for permutation means that the order matters. You see, order matters. Example, how many batting orders are possible for a 9-person baseball team? There are 9 possible choices for the first batter, 8 possible choices for the second batter, and so forth. So in other words, it's going to be 9 times 8 times 7 times 6 times 5 all the way to times 1, which would give us 362,880. The number of permutations of n elements set is n factorial. That means 9 factorial. Same answer. Now this is the formula for permutations. If NPR, where R is less than or equal to n, is the number of permutations of n elements taking R at a time, then this is my formula. NPR is equal to n factorial divided by parentheses n minus R plus parentheses factorial. And here order matters. That's a key word. So for example, I have 3 letters A, B, and C. I would like to know how many 2-letter arrangements are possible when order matters. So for example, we have AB and BA, right? These are 2 different orders because even though they got the same letters, the order matters. We have AC and we have CA. We have BC and we have CB. So the answer will be 6. 6 possible arrangements. Okay, now how can we use the formula to describe that? So it's going to be 3 permutation 2. It's going to be 3 factorial over 3 minus 2 factorial. So 3 factorial will be 3 times 2 times 1. 1 factorial will just be 1, so the answer will just be 6. Or you can do it this way. You have 3 letters and 1 arrangement. So you're going to put right 2 slots for because you want 2 letters. So how many can go here? Will be 3. If 1's chosen already, then 2 are left. So 3 times 2 is 6. Okay, now this is number 40 from page 478. From a cooler with 8 cans of different kinds of sodas, 3 are selected for 3 people. And how many ways can this be done? Okay, it's going to be 8 permutation 3. Right, so it's going to be 8 factorial or 5 factorial. So 8 will be 8 times 7 times 6 times 5 factorial. The 5 factorial cancels as 1. So we got 8 times 7 times 6 will give us 336. Or you can do it another way, right? We want, right, 3 are selected, so we're going to put 3 slots. 1, 2, 3. So the first slot, how many can go here? Will be 8. Right? After 1 is chosen, then 7 are left. After another one's chosen, 6 are left. So it'll be 8 times 7 times 6. So these two are the same. You get the same answer with 2 different ways, but these mean the same thing. Permutation, and if you do it like this, guys, with 3 blanks, and then you're gonna put the number of on the first choice, right, which was 8, and then you cannot use that same choice again because you already chose it. That's why it's going to be 8 times 7 times 6, which would be 336. Okay, we're almost done here, guys. Now comes combination. Combination means order does not matter, which will be NCR. Remember the 3 letters that I did earlier for permutations? Here, guys, let's see how many orders we have. We have AB, AC, and BC because the order does not matter. The answer is 3. So let's plug into the formula. It's going to be 3 combination 2 will be 3 factorial over 2 factorial divided by, 3 factorial divided by 2 factorial times parentheses 3 minus 2 factorial will give us 3 factorial over 2 factorial times 1 factorial. Let's simplify them. So 3 factorial will be the same thing as 3 times 2 times 1. 2 factorial was 2 times 1, and 1 factorial will just be 1. So let's begin to cancel the 2's and the 1's. So we live with 3 over 1. So the answer is 3. Okay, now this is number 46 from page 478. 4 items are to be randomly selected from the first 25 items on an assembly line in order to determine the defect rate. How many different samples of 8 items can be chosen? So it's going to be 25 combination 4, right? So we get 25 factorial over 4 factorial times 21 factorial, because 25 minus 4 is 21. We work it out, right? So we begin to cancel those, right? So we know that 4 times 3 times 2 is going to be what? 24. So that cancels with that one. So we're left with 25 times 23 times 22. So that's my answer, is 12,650. There's also, this can be put in the calculator as permutations, and it has the keys for combination and permutation. Okay. Now here's a sum up for permutations and combinations. Permutations, here are the clue words, right? And the order matters. And here are the clue words for combinations. And order does not matter. Let's do 2 more problems and then we'll be done. This is number 59 on page 478. It says a lottery game requires that you pick six different, I forgot to put the word numbers, 6 different numbers from 1 to 99. If you pick all winning numbers, you win $4 million. How many ways are there to choose 6 numbers if order is not important? You see, if order is not important, it's going to be combination, right? That means it's going to be, what, 99 combination 6? The answer will be 1,120,529,256. For part B, if order matters, then it's going to be permutation. Again, going back to the keywords will tell you which one it is. So then it'll be 99 permutation 6. This will give us 806,781,064,320. You see, it's almost like 805 billion more. Okay. Now, number 60 from page 479. It says in exercise 59, if you pick 5 out of the 6 numbers correctly, you win $5,000. In how many ways can you pick exactly 5 of the 6 winning numbers without regards to order, which means combination? Okay. So now 5 out of 6 is going to be 6 combination 5. Okay, remember, lottery requires to pick 6 numbers from 99. So we already got 5 correct numbers for the 6. So what are left is going to be 1 out of 93, right? We have to choose because they already have 6 numbers, right? And we got 5 right. But still, we have to pick another number because it requires to pick 6 numbers out of the 99. So it's going to be times 93 combination 1, right? You see, this has to be equal to 99, and this has to be the outer has to be equal to 6. Put in the calculator, right, or use a formula. We got 6 times 93, which would be 558. Okay, now this is the last problem, and then we'll be done. A financial advisor offers 8 mutual funds in a high-risk category, 7 in moderate risk category, and 10 in low risk category. An investor decides to invest 3 high-risk funds, 4 moderate risk funds, and 3 low-risk funds. How many ways can the investor do this? Okay, let's find that solution. We have 8 mutual funds, right? And we're going to pick 3. So it's going to be 8 combination 3. Then we have 7 in the moderate risk funds and the moderate risk category. So from 7, we're going to pick 4. So it'll be 7 combination 4. And lastly, from the low risk, there's 10. We want to pick 3, so it's going to be 10 combination 3. We use a formula. So here we're going to get 56 for 8 combination 3. We're going to get 35 for 7 combination 4, and then we're going to get 5. We're going to get 120 for 10 combination 3. So we multiply all those numbers, and here's my solution. So it's going to be 235,200 different possible ways. I believe that's it, guys. I want to thank you very much for staying a little bit extra, and let's take it back to Patricia.
Thank you, Mr. Azasi. Thank you, everyone, for joining us today. Probability and sets, they're always interesting and a little tricky, so I'm glad you were able to cover that for us, Mr. Azasi. I'd like to thank you all for coming. I'd like to thank Mr. Azasi for presenting, and I'd like to invite you to come and see us again next week because we're going to be going over final exam reviews from both Math 1314 and Math 1324. I hope you have a wonderful weekend and a good week. Thank you.